Our lesson today is based on a famous paper called Attention is All You Need, presented at a major conference on neural information processing systems. It was written by a team of researchers, Ashish Vaswani, Noam Shazier, Nikki Palmer, Jacob Uskerate, Lion Jones, Aidan Gomez, Lukas Kaiser, and Ilya Polosukin, working at Google and the University of Toronto. Simply put, the main systems used to translate languages used to rely on complicated networks that process information step by step or in chunks. These are called recurrent or convolutional neural networks, and they use a reader, called an encoder, and a writer, called a decoder. The best systems also used a helper tool called Attention to connect them. In easy words, the authors of this paper wondered, what if we throw away the complicated step-by-step parts entirely and only use the attention helper? This just means they created a new, simpler system called the transformer. It does not use the old step-by-step methods at all. For example, like when you can look at a whole page at once instead of reading one letter at a time, this new model can process lots of information at the same time. This makes it much faster to train. In their tests, the transformer did better than the older models. On an English to German translation test, it scored 28.4 points on the standard BLEU translation scale, which was a new record. On an English to French test, it scored 41.8 points after training for just 3.5 days on 8 graphics processing units. This is much faster and cheaper than older methods. Also, it works well for other language tasks, like labeling the parts of a sentence. How did they build it? Jacob suggested replacing the old recurrent networks with self-attention. Ashish and Ilya built the first models. Noam created key map-path parts like scaled dot product attention and multi-head attention. Nikki and Lion tested many versions and wrote the code. Lukas and Aidan helped make the code run much faster. To understand why this new system is such a big deal, let us look at how people used to translate languages before the transformer. How did the old systems work? In easy words, they used recurrent neural networks, including special types called long short-term memory and gated recurrent networks. These were the best tools for processing sequences of words. These models work step by step. This just means they read one word, update their memory, and then move to the next word, like when you read a sentence word by word and have to remember the beginning to understand the end. This step-by-step process makes it hard to do many calculations at the same time. If a sentence is very long, the computer runs out of memory and takes a long time to learn. Researchers tried tricks to make this faster, but the core limit of step-by-step reading remained. Also, researchers started using helper tools called attention mechanisms. These helpers let the model connect words, even if they are far apart in a sentence. But almost all of these systems still used the old, slow step-by-step networks as their main engine. Simply put, the transformer changes everything by throwing away the step-by-step methods completely. Instead, it relies only on attention to connect words. This allows the computer to process many words at the same time. Next, this means it trains much faster. For example, did you know it can reach top translation quality after being trained for only 12 hours on 8 graphics processing units? Other researchers also tried to make things faster by using convolutional neural networks, which process several words at once, like when you try to connect two ideas that are far apart in a book. In those older systems, the farther apart the words were, the more steps the computer had to take to connect them. This made it hard to learn connections between distant words. In the transformer, the number of steps to connect any two words is always the same, no matter how far apart they are. But this can sometimes make the details a bit blurry. To fix this, the creators used a special tool called multi-head attention, which we will discuss soon. This system uses self-attention, which is also called intra-attention. In easy words, this is a way for a single sentence to look at its own words to understand how they relate to each other. People have used self-attention for tasks like summarizing text and answering questions. But the transformer is the very first translation model to rely entirely on self-attention without using step-by-step networks or convolutions. Next, let us look at the structure of the model. Most good translation systems use a reader and a writer, which we call an encoder and a decoder. The reader takes a list of input words and turns them into a list of numbers representing their meaning. Then, the writer takes these numbers and generates the translation one word at a time. The writer is autoregressive. This just means that every time it writes a new word, it looks at the words it has already written to help it decide what comes next. In Figure 1, we see the layout, the transformer. This design uses layers of self-attention stacked on top of each other, along with simple neural network layers for both the reader, which is the encoder, and the writer, which is the coder. You can see the encoder on the left and the decoder on the right. Let us look at the encoder first. The encoder is made of a stack of 6 identical layers. In easy words, think of it like a stack of 6 blocks. Each layer has 2 smaller steps inside it. The first step is a multi-head attention helper. The second step is a simple network that processes each word position. Also, we add the original input back to the output of each step. This just means we use shortcut connections, followed by a cleanup step called layer normalization to keep the numbers stable. To make these shortcut connections work, all the parts in the model output lists of numbers with a size of 512. Next, the decoder is also made of a stack of 6 identical layers. In easy words, it is very similar to the encoder, but it has a third step. This extra step looks at the information coming from the encoder stack to help make translations. Just like before, we use shortcut connections and layer normalization for all 3 steps. Also, we changed the decoder slightly so it cannot look ahead at future words. This just means that when predicting a word, the system can only look at the words it has already written. Now, let us talk about attention. Simply put, attention is like searching for something. It takes its query, which is what we are looking for, and pairs it with keys and values, which are like tags and the actual information. The output is calculated by giving different weights to each value based on how well the query matches the keys. In Figure 2, we see 2 diagrams. The diagram on the left shows scaled dot product attention. The diagram on the right shows multi-head attention, which consists of several attention steps running at the same time. First, let us look at scaled dot product attention. The inputs are queries and keys of a certain size, which we call d sub k, and values of another size, which we call d sub v. To find the attention, we multiply the query with all the keys. Next, we divide each result by the square root of d sub k. In easy words, this division is the scaling part. Finally, we use a math step called softmax to turn these numbers into percentages, which are the weights for our values. When the computer actually does this, it processes many queries, keys, and values at the same time by grouping them into grids of numbers called matrices. We call these matrices Q, K, and V. This just means we compute the output as the softmax of Q multiplied by K transposed, divided by the square root of D sub K, and then multiplied by V. There are 2 main ways to calculate attention. One is additive attention, and the other is dot product attention. Our method is just like dot product attention, but we add the scaling step. Additive attention uses a simple neural network to match queries and keys. Both methods are similar in theory, but dot product attention is much faster and saves memory. This just means it can use highly optimized computer code for multiplying grids of numbers. When the size of the keys is small, both methods work about the same. But when the size gets larger, dot product attention without scaling starts to perform worse than additive attention. Why does this happen? We think that when the size is very large, the multiplication results become huge. Like when you multiply very large numbers and the results get out of hand, this pushes the softmax step into flat zones where the computer struggles to learn. To fix this, we scale the results by dividing them by the square root of d sub k. For example, if we assume the parts of our query and key are random numbers with a middle value of 0 and a variance of 1, then multiplying them together gives a result with a variance equal to the size of the keys. This is why the numbers grow so large. Next, let us look at multi-head attention. Instead of doing just one attention calculation with the original size of the model, we found it is much better to split the queries, keys, and values. We do this by projecting them a set number of times, which we call h times, into smaller sizes using different learned rules. On each of these smaller versions, we run the attention step at the same time. This gives us several smaller output values. Output values. Next, we glue these smaller outputs together, which is called concatenation, and process them one more time to get the final values, just like what is shown in Figure 2. Simply put, multi-head attention lets the model look at different parts of the sentence from different perspectives at the same time. If we only used one attention head, everything would get averaged together, and we would lose these details. In easy words, the multi-head attention is made by joining all the individual heads together and multiplying them by a final weight matrix. Each head is calculated by doing normal attention on the queries, keys, and values after they have been multiplied by their own weight matrices. These weight matrices are just grids of numbers that the model learns. For our model, we use 8 parallel attention heads. For each head, we set the dimension size of the keys and values to 64, which is the total dimension of 512 divided by 8. Because we make each head smaller, the total mathematical work is about the same as using one single big attention head. Next, let us look at the 3 ways we use this attention in our model. First, in encoder-decoder attention layers, the queries come from the previous decoder layer, while the keys and values come from the encoder output. This just means the decoder can look at the entire input sentence to help it translate. This is like how older translation systems used to connect their inputs and outputs. Second, the encoder has self-attention layers. Here the queries, keys, and values all come from the same place, which is the previous layer of the encoder. This allows every word in the input to look at all other words in the input to understand their relationship. Third, the decoder also has self-attention layers. This allows each word in the decoder to look at the words written before it. However, we must stop the model from looking at future words. We do this by hiding the future words, setting their values to -infinity before the softmax step. This acts like a mask, blocking illegal connections, as shown in Figure 2. Next, let us talk about position-wise feed-forward networks. Besides the attention layers, every layer in our encoder and decoder has a simple neural network. This network is applied to each position separately and in the exact same way. It is made of 2 linear steps with a rectified linear unit activation function in between. In easy words, we take the input, multiply it by a weight, add a bias, set any negative numbers to 0, and then multiply by another weight and add another bias. While these steps are the same for all positions, they use different settings from one layer to the next. You can also think of this as 2 convolutions with a filter size of 1. The size of the input and output is 512, while the inner layer is much larger, with a size of 2048. Next, let us discuss embeddings and softmax. Like other translation models, we use learned embeddings to turn words into lists of numbers of size 512. We also use a standard linear step and a softmax function to turn the decoder output into probabilities for predicting the next word. In our model, we share the same weight matrix between the embedding layers and the final linear step. In the embedding layers, we multiply these weights by the square root of the dimension size, which is the square root of 512. Let us look at Table 1, which compares different layer types. It looks at 3 features: the mathematical work done per layer, the number of steps that must be done one after another, and the longest path between any 2 words. In this table, M is the length of our sentence, D is the size of our word representations, K is the size of the convolution filter, and R is the size of a local neighborhood. First, we have self-attention. Its complexity per layer is big O of n squared times D. It only needs big O of 1 sequential steps, and its maximum path length is also big O of 1. Second, recurrent layers have a complexity of big O of n times D squared. They need big O of n sequential steps, and their maximum path length is big O of m. Third, convolutional layers have a complexity of big O of k times n times D squared. They need big O of 1 sequential steps, and their maximum path length is big O of log base k of n. Finally, restricted self-attention has a complexity of big O of r times n times D. It needs big O of 1 sequential steps, and its maximum path length is big O of m divided by r. Next, let us talk about positional encoding. Since our model does not use recurrence or convolution, it has no way of knowing the order of the words in a sentence. To fix this, we must add some information about where each word is located. This just means we add positional encodings to our word embeddings at the very beginning of the encoder and decoder. These encodings have the exact same size as the embeddings, so we can simply add them together. In this work, we use sine and cosine mathematical functions with different wave speeds. For even positions, we use a sine wave. For odd positions, we use a cosine wave. This just means each spot in our position code corresponds to a wave. The wavelengths grow in a geometric pattern from 2 pi to 10,000 times 2 pi. We chose this method because we thought it would help the model easily learn relationships between relative positions. For example, like when you know how far apart 2 notes are on a piano, no matter where you start playing. We also tried using learn position codes. and the results were almost exactly the same. We decided to stick with the WAVE method because it allows the model to handle sentences that are longer than any of the sentences it saw during training. Next, let us discuss why we choose self-attention. In this section, we compare self-attention layers with the recurrent and convolutional layers that people usually use to turn one sequence of words into another sequence of the same length. To choose the best method, we look at three important goals. First, we look at the total mathematical work done by each layer. Second, we look at how much work we can do at the same time, which we measure by the minimum number of steps that must be done one after another. Third, we look at the path length between words that are far apart. Learning connections between distant words is a big challenge. The shorter the path between any two words, the easier it is for the model to learn their relationship. As we saw in Table 1, a self-attention layer connects all words using a constant number of steps. A recurrent layer, on the other hand, requires a number of steps that grows with the length of the sentence. In terms of mathematical work, self-attention layers are faster than recurrent layers when the sentence length is smaller than the representation size. This is usually the case for the word representations used in modern translation systems, like word piece or byte pair methods. To make things faster when sentences are very long, we can limit self-attention to look only at a small group of nearby words of size r around each word. This just means the longest path between words would increase to big O of m divided by r. We want to study this idea more in the future. Next, a single convolutional layer with a filter size smaller than the sentence's length cannot connect all words together. To do this, we would need to stack many convolutional layers on top of each other, which makes the path between distant words longer. Also, convolutional layers usually require more mathematical work than recurrent layers. While special separable convolutions can reduce this work, even in the best case, their complexity is still equal to combining a self-attention layer with a feed-forward layer, which is exactly what we do in our model. In easy words, another benefit of self-attention is that it makes it easier to understand how the model thinks. When we look at how the attention is spread out, we can see that different attention heads learn to do different jobs. Many of them even seem to understand the grammar and meaning of the sentences. Next, let us talk about how we train our models. For our training data, we used a standard English to German dataset without 4.5 million sentence pairs. We turned these sentences into tokens using a method called byte pair encoding, which gave us a shared vocabulary of about 37,000 tokens. For English to French translation, we used a much larger dataset with 36 million sentences and a vocabulary of 32,000 tokens. We grouped sentences of similar lengths together. Each training group or batch contained about 25,000 input tokens and 25,000 output tokens. Next, looking at our hardware and schedule, we trained our models on a single machine with 8 graphics processing units. For our standard models, each training step took about 0.4 seconds, and we trained them for a total of 100,000 steps, which took about 12 hours. For our larger models, each step took 1 second, and we trained them for 300,000 steps, which took about 3.5 days. Also, we used a tool called the Adam Optimizer to help the model learn, with beta 1 set to 0.9, beta 2 set to 0.98, and epsilon set to 10 to the power of -9. We changed the learning rate, which is how fast the model updates its knowledge as training went on. This just means we slowly increased the learning rate for the first 4,000 steps, and then slowly decreased it as the step number grew. Next, to keep our model from just memorizing the answers, we use 3 types of regularization during training. First, we use residual dropout. This just means we randomly turn off some connections in our network. We apply this to the output of each sublayer before we add it to the input and normalize it. Also, we apply this dropout to the sum of the word representations and their position codes in both the encoder and decoder. For our basic model, we set date to 0.1, which means we randomly ignore 10% of the information. Second, we use label smoothing with a value of 0.1. This just means we tell the model not to be 100% sure about its answers during training. While this makes the model a bit more unsure of itself, it actually helps it make more accurate translations in the end. Next, let us look at our results, starting with machine translation. Simply put, our model did incredibly well. On the English to German translation test, our big model scored a 28.4 on a standard translation test called BLEU. This set a new record, beating the best previous models by more than 2 points. Training this big model took 3.5 days using 8 P100 graphics processing units. Even our basic model beat all previous models while costing much less to train. On the English to French translation test, our big model achieved a score of 41.0. This beat all previous single models while using less than 1/4 of the training cost of the previous record holder. For this French translation, we used a dropout rate of 0.1 instead of 0.3. To get our final translation results, we averaged several saved versions of our models from the end of training. For the basic model, we averaged the last 5 saved versions. For the big model, we averaged the last 20. We also used a method called beam search with a size of 4 and a length penalty of 0.6 to help choose the best translations. We set the maximum length of the output to be the input length plus 50 words, but we stopped early if the model finished sooner. Table 2 compares our results and training costs with other models. We estimate the total math operations, or floating point operations, by multiplying the training time, the number of graphics processing units used, and the processing power of each unit. For example, we used values like 2.8, 3.7, 6.0, and 9.5 teraflops for the different types of graphics cards, such as the K80, K40, M40, and P100. Next, let us look at model variations. To understand how different parts of the transformer affect its performance, we changed different settings of our basic model and measured how it affected English to German translation. In Table 3, we look at what happens when we change different parts of the transformer. We tested these changes on our English to German translation development set. Next, in the rows labeled A, we changed the number of attention heads and the size of the keys and values while keeping the overall amount of math work the same. This is like changing how many eyes the model uses to look at a sentence. Simply put, if we use only one attention head, the translation score drops by 0.9 points. However, having too many heads also makes the quality drop. This means there is a sweet spot. Also, in the rows labeled B, we see that making the key size smaller hurts the model. This just means that matching words together is not easy, and the model might need a smarter way to compare them than just a simple multiplication. Next, in the rows labeled C and D, we see that, as expected, bigger models perform better. Also, using dropout is very helpful to prevent the model from just memorizing the training data. In row E, we replace our wave-like position codes with learned position codes. In easy words, the results were almost exactly the same as our original model. Next, to see if the transformer can do other tasks, we tested it on English constituency parsing. This task is like analyzing the grammar structure of a sentence and drawing its family tree. Like when a teacher asks you to label the nouns and verbs in a sentence, the model has to label the grammar structure. This is hard because the output must follow strict grammar rules and is much longer than the input. Also, older models usually struggle with this when there is not much training data. We trained a 4-layer version of our model with a size of 1024 on about 40,000 sentences from a standard newspaper dataset. We also tried training it with a much larger dataset of 17 million sentences to help it learn even better. We used a vocabulary of 16,000 words for the small dataset and 32,000 words for the larger one. We only did a few quick tests to choose our dropout rates, learning rates, and search sizes on the Section 22 development set, keeping everything else the same as our basic translation model. In Table 4, we see how well our model performs on English grammar parsing. We tested this on Section 23 of the Wall Street Journal dataset, using a standard score called F1. First, when training only on the Wall Street Journal dataset, older models scored between 88.3 and 91.7. Our 4-layer transformer achieved 91.3. Next, when using extra unlabeled data, which is called semi-supervised learning, older models scored between 91.3 and 92.1. Here, our transformer scored 92.7, which is even better. Only a few highly specialized models that use different methods scored higher, like 93.0 or 93.3. To get these grammar parsing results, we allowed the model to make longer outputs, up to the input length plus 300 words. We set our beam search size to 21 and used an alpha value of 0.3. In easy words, even though we did not tune our model specifically for this grammar task, it did surprisingly well. It beat almost all previous models except for one called the Recurrent Neural Network Grammar. Also, unlike older recurrent sequence-to-sequence models, our transformer did better than the Berkeley parser, even we only trained it on the small dataset of 40,000 sentences. To conclude, we presented the transformer, which is the first translation model built entirely on attention. Simply put, we replaced the usual recurrent layers with multi-headed self-attention. For translation, this means the transformer learns much faster than older models that use recurrent or convolutional layers. Also, it set new records for both English to German and English to French translations. In fact, our best model even beat groups of other models combined. We are excited about the future of attention. We want to apply it to other things besides text, like images, audio, and video. We also want it to make the model generate words even faster by doing less step-by-step work. If you want to try it yourself, our code is open to everyone on GitHub at TensorFlow/Tensor2Tensor. Also, we want to thank Nal Kalkbrenner and Stefan Gauss for their helpful feedback and ideas. Finally, here are the first 4 references we used. Number 1. Jimmy Leibar, Jamie Ryan Quiros, and Jeffrey E. Hinton. Layer normalization. Archive preprint. Archive number 1607.06450, 2016. Number 2. Dmitry Bogdanov, Kyunghun Cho, and Yoshua Bengio. Neural Machine Translation by Jointly Learning to Align and Translate. Computing Research Repository, Abstract 1409.0473, 2014. Number 3. Denny Britz, Anna Golgi, Mengthang Luong, and Kwok V. Lee. Massive Exploration of Neural Machine Translation Architectures. Computing Research Repository, Abstract 1703.03906, 2017. Number 4. Jianpeng Cheng, Li Dong, and Mirella Lapata. Long Short-Term Memory Networks for Machine Reading. Archive preprint, archive number 1601.06733, 2016.